We often underestimate our reliance on electricity and electronic devices. Both these things rely upon a property or a process called electrical conduction. So conduction is vital for the functioning of our modern society, and it also is a topic that physicists love to teach. So naturally today I'm going to talk to you about something different. Well, related, but different. I want to talk about a different process called superconduction and the phenomenon, superconductivity, and the real-world devices or materials that display the behavior, superconductors. Two things make superconductors different from the ordinary conductors we have in our homes and offices all around us. One, collective behavior. Superconductivity results from the collective behavior of an immense number of free electrons in a metal. Bob the Bishop is thinking about it. He's telling us that we should consider electrons in pairs, each with opposite directions of a property called spin. And these pairs overlap each other to a great extent, so much so that they act like one big macromolecule. Two, superconductors require extreme conditions, very low temperatures, or very high pressures. When originally discovered in 1911 in mercury, the material, mercury, it was at atmospheric pressure, but very close to absolute zero temperature, which is negative 460 degrees Fahrenheit. We now know of materials that will superconduct at much higher temperatures, but we have to put them under very extreme pressures to get them to do it. So extreme conditions. Now, in normal conduction that we are familiar with, you have a complete circuit, you have conducting wires with free electrons, a battery pushes on those electrons in a preferred direction, but as individual electrons, they cannot avoid a process known as scattering, which impedes their flow. And it's this scattering that gives rise to what we call resistance in the circuit. And anytime you have resistance in an electric circuit, you will ultimately convert electrical energy into other forms like heat and light. Now, sometimes we want to do that with a circuit, but often we do not. In superconduction, the collective behavior of all those free electrons means that they can avoid all scattering. And in avoiding all scattering, they exhibit zero electric resistance, zero. And you just think about the technological applications that would go with zero resistance in a circuit. Some of them are shown and listed here. But there's one more interesting collective behavior in superconductors that you have to see to believe. And it has to do with their behavior in a magnetic field. What they do is that they expel magnetic field from part of the body of the superconductor, while at the same time locking magnetic field into place into other parts. So you could see this in action in our own physics and astronomy department here at OWU. We made a video. We took a so-called high-temperature superconductor out of a bath of liquid nitrogen at a balmy negative 321 degrees Fahrenheit and put it near a couple of different permanent magnets. There's a square permanent magnet on the left. Magnetic field exclusion means the superconductor floats on top of the magnet or levitates. And it's robust. It can hold more than twice its own weight and still levitate. Interestingly, you take that same superconductor and put it in the more symmetric magnetic field of the ring magnet on the right, and the superconductor will both levitate and rotate. And because of magnetic field locking, you can turn the whole thing upside down. Turn the magnets over, bring the superconductor up from underneath, and it will still levitate. Now, as cool, literally, as this is, superconductivity has one big outstanding challenge that we need to conquer if it's going to become part of our daily lives. We need to find or design a compound that superconducts at room temperature and atmospheric pressure. It will be important work, and I have some confidence that we can do it. It will undoubtedly require a collective effort of many talented people. And it's my hope as an OWU educator that some of you will be part of that endeavor. Thank you.